Yes guys, today we're going to be deriving the projectile formulae. Essentially we're going to be using a lot of SUVAT to derive some much useful shortcuts when working with projectiles. So if we draw a projectile that's been projected from this point with, let's say, speed u, starts at point 0 and travels a horizontal distance x, and it does reach a max height here, so let's call this its max height. We said it's projected from u meters second at, let's say, an angle alpha to the horizontal, and this is time t. So time t is when it hits the back in level with the surface it was projected from. So the first formula we're going to derive is the maximum height. So if we start by listing our SUVAT variables with both vertical and horizontal, so ux, vx, a and t. So sy is what we're trying to work out. U, well, that's just this here, so opposite over hypotenuse, we have u sine alpha. Final at the maximum height, well, if you see how the particle is acting, well, at this point it's got no vertical component, it's just acting horizontally. So what we say is that it's got 0 vertical velocity, and the acceleration, well, if we're working solely upwards and downwards, and we say that we're taking upwards as positive, then our acceleration is minus g, and t is, well, that is just, well, just let's call it, let's leave that for now actually. Now if we go over to the other side, we've got, actually we can leave that for now. So alright, we've got s, we've got u, we've got v, we've got a. So we can use the formula v squared equals u squared plus 2as, and we're trying to find out s. So if we start off by subbing what we know, u squared equals 0 squared equals u squared, so that's u squared sine squared alpha plus 2 minus g, which in this case, actually we can leave it as g, so minus 2gs. Rearrange for s, because that's what our maximum height is. So we have 2gs equals u squared sine squared alpha, then s equals u squared over sine squared alpha all over 2g. Second formula we want to derive is the time at maximum height. Should we say time taken to get to maximum height? Taken to get to max height. So again, keeping pretty much everything the same, we just copy this down. So now we're working with an equation in terms of t. So what we use is this formula: s equals ut plus a half at squared. And we know what s is now anyways. Actually, since we don't know s, we can use v equals u plus at. v equals u plus at. So v is 0, u is 0, u sine alpha, at is minus gt. So t equals u sine alpha over g. And this is the time taken to get to max height. Third equation we derive, which is not much for derivation, is time of motion. Well, we define motion in this situation from here all the way to here. Well, since this projectile is modeled as a parabola, we can just double the time from here to here to get all of this, which is just 2 times this t we worked out. So t equals 2u sine alpha over g. Nice. Now, what we're trying to do, we are trying to find out another formula, so the range of motion. So let's copy down our SUVATs. So ultimately, we're going to be working on the right hand side now with our horizontal component. So we have u cos alpha. Final velocity we don't know. Acceleration we do know, which is 0. Time taken, well, we just derived that, so that's 2u sine alpha all over g. And this stuff can all go, it's not really relevant right now. So applying SUVAT on the horizontal components, where we've got s, we've got u, we've got a, we've got t. So again, s equals ut plus a half at squared. Well, we know that a is 0, so all of this just becomes 0, so we left with s equals ut, so we have x equals u cos alpha multiplied by 2u sine alpha all over g. 2 u's multiplied become u squared, so we have u squared, and then we have 2 sine alpha cos alpha. Well, going back to our double angular formulae, we know that this is just sine 2 alpha, and the denominator stays the same, so we just have g. So that's the fourth equation derived. And now on to the final one. We call this the trajectory of motion. So this involves essentially just, I think it's, well, it's just take any point, let's say the point xy on the path of the projectile. What can we find from the equation we're going to derive? So let's just get in everything we know. S equals u v a t, y, this is minus g, let's call this t, and then sx, ux, vx, a, t, 0, t. We know what the initial speeds are, so u sine alpha, u cos alpha. And we're trying to find this and this. Let's call this y and x. So using s equals ut plus half at squared, we have y equals u sine alpha t plus a half acceleration, so that's minus a half g t squared. Then here we have, again we're using the same super equation, but we have x equals u cos alpha t. Okay. Plus a half a t squared, where a is 0, so that doesn't really help us. So what was it? S equals ut. Now how do we link this? Well, both these equations share the same time, so we can arrange this one for t. So we have x over u cos alpha. Now sub this into our vertical equation, so we have u sine alpha x over u cos alpha minus a half g x squared over u squared cos squared alpha. Now if you simplify this, so y equals u over u cancels, cancel. So we're left with sine over cos, which is tan alpha, x, so x tan alpha, minus a half, well, g stays the same, minus half g, x squared is fine, over u squared, and then cos squared, well that just becomes sec squared alpha. You can tidy this up a bit further, so y equals x tan alpha minus g x squared over 2u squared, and sec squared using our trig identities is tan squared alpha. And that is the last identity shown. Just check, is that alright? Yes it is. Perfect. We just derived 5 useful projectile equations. Hope this helps. See you in the next.